A single particle of light is traveling toward you from the edge of the universe. This photon began its existence billions of years ago inside a dying star, and its journey holds the key to understanding our deepest cosmic connections. By the end of this story, you will see the night sky not as a static picture, but as a living historical document written in light. How did this photon survive a gauntlet of cosmic hazards and the stretching of space itself to reach your eye? What does its ancient message reveal about our place in the cosmos? What forgotten story does the light from a single star tell you? Deep within the star's searing heart, a titanic struggle unfolds. Atoms of hydrogen, crushed together by pressures beyond comprehension, surrender their individual identities and fuse into something new. This is nuclear fusion, the engine of stars, and with each union, an immense burst of energy is born. That energy manifests as a photon, but not the gentle, visible light we know. This newborn is a furious spike of gamma radiation, the most energetic form of light in the universe. Its life begins not with freedom, but with immediate imprisonment. The core is a superheated plasma so dense that light cannot travel in a straight line. Our photon is immediately captured, absorbed by a waiting atom, only to be spat back out a tiny instant later in a random new direction. This frantic dance of absorption and re-emission happens over and over and over again. A single step in this subatomic waltz might cover less than a centimeter. To travel from the stellar core to the surface, a journey of hundreds of thousands of kilometers, becomes a random walk of staggering patience. What feels like a blinding flash of creation from the outside is, from the photon's perspective, a slow-motion prison break lasting tens of thousands of years. It is a relentless game of cosmic pinball where every bounce saps a tiny bit of its ferocious energy, gradually transforming that initial gamma ray into a less energetic form of light. This immense struggle is the forgotten prologue to every twinkle in the night sky. After an eternity of chaos, the photon finally reaches the star's outer layer, a place where the density of matter finally thins out. In one final, decisive interaction, it is emitted outward, not into another atom, but into the waiting void. For the first time in its long existence, it is truly free, streaking into the interstellar darkness at the ultimate speed. Its long confinement is over, but an even greater journey is just beginning. Freedom arrives in a single, explosive instant. After its tens of thousands of year imprisonment, the photon bursts from the star's searing surface, the photosphere, and into the open frontier of space. In that decisive moment, the star permanently imprints its identity upon this tiny traveler. The star's immense surface temperature, a measure of its ferocious nuclear energy, dictates the photon's final form. A hotter star forges photons of higher energy, which we perceive as blue or white light. A cooler, more tranquil star releases lower energy photons, glowing with a red or orange hue. The specific color you see in a star is not a random choice, but a direct message about its physical nature, a cosmic fingerprint carried by every particle of light that leaves its surface. Now set for its epic voyage, the photon accelerates to the universe's ultimate speed limit, the constant speed of light. It streaks away, a solitary voyager aimed at the profound emptiness between stars. Its path is now a perfectly straight line, a vector of information shooting through the void, carrying the ancient story of its birth and the unique signature of the star it has finally and forever left behind. This photon is one of the universe's most profound riddles, a tiny traveler that is both a particle and a wave. To grasp its epic voyage, we must first understand this strange duality. As a particle, it is a fundamental packet of pure energy, a discrete piece of light with no mass whatsoever. It is the ultimate minimalist traveler, carrying nothing but its own energy and moving forever at the universe's ultimate speed limit. Yet, simultaneously, this same photon behaves as a wave, rippling through the fabric of space with a specific frequency and wavelength. It is this wave-like property that our eyes ultimately interpret as color. The specific energy of this photon, forged in the heart of its star, dictates whether we will one day perceive it as a brilliant blue, a fiery red, or any color in between. This wave-particle duality is the bizarre, beautiful heart of quantum mechanics, and it defines every single interaction this photon will have on its long journey. It explains how light can be focused like a particle, yet also diffract and spread out like a wave. This dual identity leads to a reality even more difficult to comprehend. Because the photon travels at the speed of light, the rules of our universe change for it. According to Einstein's theory of relativity, as an object approaches the speed of light, time for that object slows down relative to everything else. For the photon itself, traveling at that ultimate velocity, time does not pass at all. From the photon's own perspective, if it could have one, its multi-billion-year journey across the cosmos is not a long, epic saga. It is instantaneous. The moment it bursts free from its star is the same moment it arrives in your eye. No matter how much distance lies between, it experiences no time, no distance. Its entire existence, from creation to destruction, is a single, timeless event. This underscores the profound chasm between our human experience of a vast, ancient universe and the photon's reality of a universe without time. With this strange nature in mind, we can now follow it into the great expanse, a journey that is, for us, filled with eons of potential encounters. Its speed is a universal constant, locked at 299,792,458 meters every single second. At this incredible velocity, our photon could complete more than 7 full laps around the Earth in the time it takes you to blink. This is not merely fast travel, it is the ultimate speed limit of the cosmos, an unbreakable rule woven into the fabric of reality itself. Whether the star that created it was rushing toward us or flying away, the speed of this photon remains exactly the same from any perspective. This constancy transforms the vast emptiness of space into a cosmic time machine. The light from our nearest galactic neighbor, the Andromeda Galaxy, did not simply cross a great distance to reach us. It embarked on a journey that began 2.5 million years ago when early hominids walked the Earth. Every star we see is a living relic, and every photon is a messenger from a forgotten age. For the vast majority of its existence, our photon is engaged in this silent, solitary sprint. It streaks through the interstellar void on a perfect, straight-line trajectory, a single data point racing across the galactic stage. But what happens when this perfect path is interrupted? What cosmic obstacles lie in wait to challenge its relentless journey? But this perfect, straight-line path is an illusion. For billions of years, our photon races through a near-perfect vacuum, an emptiness so profound it defies human comprehension. The best vacuums we can create in laboratories on Earth are cluttered, noisy environments compared to the void between the stars. Here, in the interstellar darkness, a single cubic centimeter of space might contain only a single, lonely atom. This means our photon can travel for thousands of years, covering distances so vast they numb the mind, without ever coming close to another particle. This is the silent, dominant reality of the cosmos, a universe composed mostly of nothing at all. Yet this emptiness is not truly empty. It is a vibrant sea of invisible fields. The gravitational pull of every star, planet, and galaxy permeates this space, bending the very fabric of the universe. Immense magnetic fields, generated by the motions of cosmic plasma, thread through the darkness. And everywhere, the Higgs field gives mass to the fundamental particles the photon might never even meet. Our traveler, being massless, sails through all of these fields without slowing or deviating from its path. It is a ghost ship on a phantom sea, utterly alone yet surrounded by the invisible forces that sculpt the cosmos. This immense, quiet stretch of the journey is the rule, not the exception. It is a testament to the sheer scale of the universe, a scale where even light must spend eons in solitary transit. But this solitude is not absolute, for the stage upon which it travels is not a static one. The fabric of spacetime itself is dynamic, and it is here, in the deepest void, that the most subtle and powerful influences await. The first true test of our photon's journey is not a dramatic collision, but a silent, drifting cloud. These vast formations of interstellar dust and gas, the very nurseries where new stars are born, become a labyrinth for ancient light. As our traveler approaches, it enters a realm where emptiness gives way to a sparse but significant haze of microscopic dust grains and lonely atoms. The photon does not simply bounce off these obstacles. Instead, it engages in a delicate quantum dance dictated by its wave-like nature. The specific energy or color of the photon is everything. If its wavelength perfectly matches the resonant frequency of an atom in the cloud, that atom can reach out and capture it. In that instant, the photon's epic journey simply ends. Its energy is absorbed, transformed into a slight increase in the jiggling motion of the gas atom, a tiny bit of heat lost to the cold of space. Sometimes, the atom will later release a new photon, but this one is a different entity, born in the cloud and sent off in a random, unpredictable direction, its original message from the distant star forever lost. This is the silent, filtering reality of the cosmos. It is why we see dark patches in the Milky Way, not as holes in the galaxy, but as immense clouds of dust blocking the light from the stars behind them. They are cosmic curtains, and only the lucky photons, those whose colors do not match the cloud's appetite, pass through unscathed. Our photon, by a twist of cosmic fate, is one of these fortunate ones. It slips through the microscopic gaps in the cloud, its path and its story still perfectly intact, continuing its voyage towards a destination it cannot yet know. Its straight-line trajectory is an illusion, a convenience that only holds true in an empty universe. But our universe is far from empty. It is a tapestry of mass and energy that warps the very stage upon which the photon travels. As it speeds through the cosmos, it may pass near a truly massive object, a galaxy cluster containing trillions of stars. According to Einstein's theory of general relativity, such a concentration of mass does not simply pull on the photon with an invisible force. Instead, it warps the fabric of spacetime itself, creating a kind of cosmic depression. The photon, simply following the shortest path through this curved geometry, finds its path subtly bent. This phenomenon is gravitational lensing, the universe's own telescope. The photon itself feels nothing. It experiences no force, and its speed remains perfectly constant. It is merely following the contours of the road, a road that has been bent by immense weight. For astronomers, this effect is transformative. A massive galaxy cluster can act as a natural lens, magnifying the light from far more distant galaxies hiding behind it, allowing us to see objects that would otherwise be permanently invisible. For our single photon, this might mean a slight detour, a graceful curve added to its billions of years of travel. Its message from the ancient star remains perfectly intact, but the path it took to deliver that message was gently guided by the hidden architecture of the cosmos, a cosmic guidance system written into the fabric of reality. Yet this journey is not merely a passage through space, but also a voyage through time itself. The very fabric through which our photon travels is not static, it is relentlessly expanding. This cosmic expansion introduces the most profound transformation our traveler will ever face, a phenomenon known as cosmological redshift. As the photon streaks across billions of light years, the space between galaxies is continuously stretching. Imagine our photon's wavelength as a wave on a vast cosmic rubber sheet. As the sheet is steadily pulled taut in all directions, the wave itself is forced to stretch out, its peaks and troughs moving farther apart. This lengthening of its wavelength is the redshift. A brilliant blue photon forged in a hot, young star does not simply fade. It is systematically and gradually shifted toward the red end of the spectrum. If its journey is long enough, it may be stretched entirely out of the visible range, becoming an invisible infrared photon by the time it nears our telescopes. This is not a loss of energy through collisions, but a fundamental dilution of its energy caused by the stretching of the cosmos. The photon carries this change as a permanent, unalterable record. For astronomers, this redshift is a cosmic odosimeter. By measuring precisely how much a photon's light has been stretched, we can calculate not just the distance to its home galaxy, but the duration of its incredible journey. The deep red hue of a distant galaxy is not its true color. It is the tired, stretched signature of ancient light, a direct measure of how much the universe has expanded since that photon began its voyage. This silent, continuous transformation means that every photon of ancient light arriving at our eyes is more than a messenger from a star. It is a living fossil, its very color encoding the entire history of cosmic expansion. It is tangible proof that we live not in a fixed, unchanging universe, but in a dynamic, evolving cosmos, and that every star we see tells a story written not just in light, but in the stretching of space-time itself. So we arrive at the most profound paradox of this entire epic. The photon has crossed billions of years of cosmic history, yet it has experienced none of it. From our perspective, anchored in a slower reality, we watch this ancient light complete an epic saga. But from the photon's own reference frame, a consequence of special relativity that defies all intuition, its entire existence is compressed into a single, timeless point. There is no journey for it. There is no passage of years, no lonely transit through dust clouds, no graceful arc around galaxies. The moment it bursts free from its dying star is, from its own perspective, the very same moment it is absorbed by the retina in your eye. The beginning and the end are simultaneous. It is a life story written on a page with no space between the first word and the last. This is the ultimate meaning of traveling at the universe's ultimate speed. As you approach light speed, time itself slows to a halt. For the massless photon, which knows no other speed, time does not simply slow down, it ceases to pass altogether. The billions of years that shape galaxies and civilizations are, for this tiny traveler, a zero. It lives and dies in an instant that lasts for eternity. How do we even begin to reconcile these two truths? Our reality is one of sequence, of cause and effect stretched across the vast canvas of cosmic time. But the photon's reality is one of pure, timeless connection. It challenges our most basic assumptions about what existence even means. Is its journey a long, storied pilgrimage, or is it a simple, immediate bridge between 2 points in space-time? The universe, it seems, insists that both stories are equally true, revealing a reality far stranger and more wonderful than our everyday intuition allows. Before our photon can even contemplate the void between galaxies, it must first escape its own bustling Metropolis. This is its home galaxy, a spinning disk of billions of stars, vast clouds of gas, and immense curtains of cosmic dust. The density here is 1,000 times greater than the lonely interstellar voids it has already crossed. Its path is no longer a clean, straight line, but a frantic, unpredictable dance through a celestial pinball machine. Every star it passes, even by a wide margin, exerts a tiny gravitational tug, imperceptibly bending its trajectory. It must slip through the turbulent nurseries of newborn stars, regions glowing with intense radiation that could easily scatter a lesser particle of light. It might even skirt the edge of a supernova remnant, the expanding shell of a stellar explosion that seeds the galaxy with newly forged heavy elements. All the while, the collective gravitational pull of the galaxy's core, often anchored by a supermassive black hole of almost unimaginable scale, acts as a constant, distant anchor, trying to curve its path inward. For every photon that successfully escapes this galactic maze, countless others are absorbed by dust or gravitationally slung into orbits from which they will never leave. But our traveler, through a perfect alignment of chance and physics, navigates this stellar gauntlet. It climbs out of the galaxy's gravitational well, slipping free of the spiral arms and the halo of dark matter that binds it all together. With this successful exit, its status changes forever. It is no longer just a messenger from a star, but an ambassador from an entire galaxy, now sailing into the profound and nearly empty expanse of the intergalactic medium. The greatest stretch of its journey now lies ahead. Freedom from the galaxy does not mean the journey is over. It means entering a different kind of emptiness, a void so profound it defies all human scales of comparison. The Photon now sails through the intergalactic medium, a cosmic desert where the average density of matter is 1,000,000 times lower than the sparse regions within its home galaxy. Here, a single atom might occupy a space the size of a small closet. For millions of years, our traveler streaks through this near-perfect nothingness, a solitary data point in an ocean of darkness. The only signs of other life are the faint, fuzzy glows of distant island universes, each one a collection of billions of stars now reduced to a soft, unreachable smudge of light in the infinite black. This is not the cold of deep space as we might imagine it. The temperature here is not absolute zero. Instead, the entire void is gently warmed to just a few degrees above that ultimate cold by the faint, omnipresent echo of the Big Bang itself, a thermal memory from the birth of the cosmos that fills every cubic inch of nothing. This immense, quiet segment of the voyage is the rule, not the exception. It reveals a startling truth about our universe, that most of its volume is not in the brilliant cities of stars, but in these vast, underpopulated hinterlands. The Photon's lonely cruise through the cosmic abyss is a silent testament to the sheer, overwhelming scale of existence, a scale where even light must spend eons in utter solitude, its ancient message still intact, racing toward a destination that remains an unimaginable distance away. This single photon is a perfect time capsule, sealed the instant it left its star. Every property it possesses, from its precise energy to its direction of travel, was locked in place billions of years ago, creating an unaltered snapshot of a moment in cosmic history. When we finally capture this ancient light, we are not merely seeing a distant point of light. We are opening a letter mailed to us before our planet even existed. The most extreme examples of this are quasars, the blazing cores of young galaxies, powered by supermassive black holes feasting on immense amounts of gas. The light from a quasar that arrives in our telescopes tonight may have begun its journey when the universe was just a fraction of its current age, a time when the first galaxies were still assembling themselves from the primordial fog. That photon carries within it the chemical signature of the gas it passed through, the ferocious temperature of the accretion disk that forged it, and even clues about the magnetic fields that shaped its final path. In this way, astronomers are not simply stargazers. They are cosmic archaeologists sifting through the steady rain of ancient photons to reconstruct the biography of the universe itself. Our traveling photon is one such pristine artifact. Its specific color tells us the exact temperature of its stellar parent. Its unchanging direction of travel, despite gravitational lensing, points back to its origin with perfect fidelity. Even its polarization, the specific orientation of its wave pattern, can reveal the magnetic environment it encountered at its birth. Each of these properties is a piece of historical data, frozen in time since its departure. This tiny traveler is therefore more than just light. It is a single, invaluable data point in the grand story of cosmic evolution, a direct witness to an era long gone, now delivering its testimony directly to us. But even after escaping its galaxy, the Photon faced a universe cloaked in shadow. In the deepest reaches of time, the cosmos was not a transparent void, but a pervasive fog of neutral hydrogen gas. This was the cosmic dark ages, an era when the universe was a vast, unlit expanse, and light could not travel far before being swallowed by this primordial mist. The end of this era was a violent, beautiful transformation called reionization. The first stars and galaxies ignited, their intense ultraviolet radiation flooding the cosmos, stripping electrons from the hydrogen atoms and burning the fog away. For a photon beginning its journey in that epoch, its survival was a matter of cosmic lottery. It had to be the right kind of light with just the right energy to slip through this diffuse barrier without being absorbed and lost forever. Even today, the intergalactic medium is not a perfect vacuum. It is a ghostly sea of ionized gas and plasma, a relic of that great clearing. This tenuous material can still scatter or absorb photons, particularly at very specific wavelengths. The fact that our photon made it through means it is a specific type of messenger, its energy carefully tuned by the universe itself to pass through these diffuse filters. Its successful voyage means it carries within it an unblemished record from a time when the universe was fundamentally rewiring itself, a pristine survivor from the age when the cosmic dawn burned away the darkness. Yet for all its resilience, the photon now moves through a universe governed by a hidden hand. The vast halos of dark matter that envelop every galaxy and cluster exert a gravitational pull far exceeding that of all the visible stars and gas combined. This mysterious substance does not block the photon's path or absorb its energy, for it does not interact with light in any way we have yet detected. Its presence is felt only through gravity, the gentle but persistent bending of the spacetime through which our traveler moves. When the photon's path curves around a massive galaxy cluster, that graceful arc is not solely due to the glittering cities of stars. The primary architect of that detour is the immense, invisible sphere of dark matter in which the entire cluster is embedded. This unseen mass acts as a cosmic lens of unimaginable scale, sculpting the paths of light from the distant universe. The photon, in its unwavering flight, becomes a silent probe of this darkness. Its final trajectory, when we trace it back, reveals not just the location of visible matter, but the true, hidden distribution of mass in the cosmos. Every time we observe a gravitationally lensed galaxy, we are seeing light that has been guided by a roadmap we cannot see, a map written in the language of gravity by the dominant, unseen component of our universe. The photon's journey is therefore a continuous dialogue with the dark, its straightest possible line forever being rewritten by the presence of a mystery that shapes everything. This ancient light is never truly alone in the void. For its entire multi-billion-year voyage, our photon has been immersed in a faint cosmic glow that permeates every corner of the universe, the cosmic microwave background. This is the oldest light in existence, the cooled and stretched afterglow of the universe's fiery birth. When our photon began its journey from that distant star, this background radiation was already ancient, a relic from a time when the cosmos was a mere 380,000 years old, a hot, dense plasma of particles and energy that finally cooled enough for the first stable atoms to form and for light to travel freely. That first flash of light has been traveling ever since, its waves stretched by the expanding universe from visible heat into the microwave part of the spectrum, a cold whisper just a few degrees above absolute zero. Our star-born photon, with its specific high-energy signature, sails through this sea of primordial light like a modern speedboat through a placid, ancient ocean. They do not collide or interfere in any significant way, yet the background is always there, a constant, humming testament to how it all began. This faint microwave static is the ultimate origin story for every photon that has ever existed. The brilliant light from our star, the gentle glow of a candle, even the light bouncing from this screen into your eyes, all of their ancestral lines can be traced back to that same primordial fireball. Our photon's epic journey is just one single, remarkable story among an infinite number of others that all started in that same initial burst of creation. It is a later chapter in a cosmic saga that began with the first light, a reminder that every gleam and glimmer in the darkness shares a common, profound inheritance. After billions of years sailing the intergalactic void, a new island of light swells ahead. This is the Milky Way, our home galaxy, and our photon is now falling into its final gravitational embrace. Its approach is not a simple plunge, but a careful navigation through the galaxy's outer halo, a vast sphere of ancient stars and mysterious dark matter that extends far beyond the visible spiral. Here, the density of space begins to thicken once more. The photon weaves through globular clusters, dense cities of stars that are some of the oldest structures in the galaxy, their collective gravity providing subtle course corrections. It is re-entering a realm of substance and light after an almost unimaginable solitude. This is the final major leg of its journey within a galactic structure, a homecoming to a place it has never been. As it descends from the halo and pierces the galactic plane, it enters the bustling disk of the Milky Way. The environment transforms completely. The sparse emptiness gives way to a crowded stellar highway. It now races past stars that are our relatively close neighbors, skirting the brilliant edges of vast nebulae where new solar systems are coalescing from glowing gas and dust. Every moment presents a new potential hazard, a chance encounter with a dust grain that could end its epic message. The space here is filled with a local background of photons, the combined light of our own sun, and the reflected glow from countless planets. It is a cosmic cacophony compared to the silent deep, yet our traveler from afar remains distinct. Its unique redshift, a permanent stretch imprinted by the expanding universe, and its precise spectral signature act as an immutable passport. These properties mark it unequivocally as an extragalactic visitor, an ambassador from a distant shore. This final approach is the last chapter of its long-distance travel, bringing it into the familiar stellar neighborhood we call home. The final destination is now almost within reach, but the most delicate part of the voyage still lies ahead. The photon now pierces the inner boundary of our solar system, a domain utterly ruled by the light and gravity of our sun. It screams past the frozen orbits of the outer gas giants, their immense scale rendered insignificant by its incredible velocity. These worlds are but fleeting waypoints in a journey measured in light years. Now it swims against a river of local light, photons born of our own sun just minutes ago. This modern light creates a brilliant background hum, but our ancient traveler remains distinct, its redshifted signature a clear badge of its extragalactic origin. Its path takes it through the zodiacal cloud, a diffused disk of fine dust particles lingering from the solar system's formation. These tiny grains, illuminated by the sun as the faint glow of the zodiacal light on a dark earthly night, are a final scattering hazard. A single impact with one of these motes would permanently erase its message, but fortune favors this tiny voyager once more. It slips through the microscopic gaps, its trajectory unwavering. Ahead, a small, blue-white marble grows from a point of light into a distinct world. The photon's vector, set with impossible precision billions of years ago, is now locked onto the third planet. After an epic voyage spanning the lifetime of galaxies, its target is finally in sight. This speck of rock and water, teeming with a complex biosphere utterly unknown to the star that birthed the photon, is the final destination. The mission is nearly complete. The blue marble now fills its entire view, a swirling canvas of white clouds and deep oceans. But between the photon and its final destination lies one last gauntlet, Earth's dynamic and protective atmosphere. This final descent is the most perilous part of its entire multi-billion-year voyage. It first slices into the exosphere, a tenuous fringe where atoms escape into space, feeling almost like the void it has long traversed. But then it punches into the denser layers, a turbulent ocean of gas that presents a final, decisive filter. Here, it is no longer navigating the grand emptiness of space, but a storm of molecules, primarily nitrogen and oxygen. Each of these tiny particles presents a potential ending. The photon's fate is now entirely dictated by its color, the very identity forged in its stellar furnace so long ago. If it is a blue photon, it faces almost certain doom. The size of air molecules is perfect for scattering this specific wavelength, bouncing it around the sky in a frantic, random dance. This very process is what paints our daytime sky blue, a beautiful phenomenon that spells the end for countless blue messengers from the cosmos. Their ancient journeys conclude not on the ground, but in a diffuse glow overhead, their stories lost to the air. Conversely, if our traveler is an infrared photon carrying the warmth of its distant star, it faces a different threat. Molecules like carbon dioxide and water vapor, the so-called greenhouse gases, are primed to absorb its energy directly, converting the photon's message into a slight, imperceptible warming of the atmosphere. To succeed, to complete its epic delivery, the photon must be of a very specific type. It must fall within the visible range, yet avoid the blue scattering fate. It needs to be a photon of yellow or green, or most reliably, red light. These wavelengths slip through the atmospheric barrier with minimal interference, passing through what astronomers call the atmospheric window. This is the final, ruthless quality check after an odyssey across the universe. In this last millisecond of its journey, the photon's entire purpose hinges on a characteristic decided at its birth. It is a cosmic lottery with the sky itself as the final judge, determining whether this ancient light will finally be seen or fade forever into the background hum of our world. The final barrier is crossed. For a photon that has slipped through the atmospheric window, the last fraction of a second of its multi-billion-year journey begins. Its target is now absolute, rushing up to meet it. In one reality, this ancient traveler streaks toward the polished mirror of a telescope, a technological eye pointed at the heavens. In another, it plunges into the dark, organic sphere of a human eye gazing upward. In either case, this is the moment of impact, the final, decisive interaction for which the entire cosmos has been the stage. The photon's existence as a free particle ends here in a final, purposeful surrender of its energy. When it strikes the silvered surface of a telescope mirror, it does not bounce away. It is absorbed, and its precise energy is converted into a minuscule electrical signal. This tiny pulse of current is utterly insignificant on its own, but it is never alone. It joins a torrent of millions of other such signals from its sibling photons, all collected over minutes or hours. Together, they are woven by a computer into a single, coherent digital image, a picture that an astronomer will later study to decode the secrets of a distant galaxy. The photon's story becomes a single pixel in a grand cosmic portrait, but when the destination is a living eye, the process is even more profound. The photon, perhaps one of a handful from a faint star, penetrates the lens and plunges into the retina. There it is captured by a single photoreceptor cell, a microscopic biological sensor. The photon's energy triggers a precise chemical reaction within the cell, a cascade that ends with an electrical impulse racing down the optic nerve. Your brain receives this signal and interprets it not as a chemical change or an electrical spike, but as a simple, undeniable point of light in the darkness. That single spark of perception in your mind is the ultimate purpose of this epic voyage. The entire journey, from nuclear fusion to gravitational lensing, from the stretching of space-time to the gauntlet of the atmosphere, was all for this. To transfer a packet of information, a story billions of years old, into a conscious mind capable of wondering about its origin. The star, the galaxy, the void, all find their meaning in this final connection. The long story that began in a stellar core concludes not with a bang, but with a quiet spark of awareness, bridging the vast, impersonal cosmos to the intimate world of thought and wonder. This tiny particle of light is a cosmic messenger, its entire being a compact data packet from a distant era. Its most obvious clue is its color, the precise wavelength imprinted upon it by the temperature of its stellar birthplace. A star's surface temperature, a direct result of its ferocious nuclear fires, dictates the exact energy of the photons it emits. By measuring this color with immense precision, astronomers can instantly read the surface temperature of a star trillions of kilometers away, classifying it as a scorching blue giant or a cooler red dwarf. But the data runs far deeper. When this light is spread out into a full spectrum, a unique barcode of dark and bright lines appears. These spectral lines are the fingerprints of specific elements. Each element in the star's outer atmosphere absorbs light at very specific wavelengths, creating a telltale pattern that reveals the star's chemical composition. We can know with certainty that a star is rich in iron, silicon, or oxygen, not by traveling there, but by patiently decoding the subtle gaps in the ancient light that arrives here. The intensity of this light, its sheer brightness as it reaches us, carries another vital piece of the puzzle. If we know a star's intrinsic power, its true luminosity, then measuring how dim it appears from Earth allows us to calculate its distance with extraordinary accuracy. This is the cornerstone of the cosmic distance ladder, allowing us to map the universe. The photon's journey itself becomes a measuring tape billions of light years long. Furthermore, the subtle orientation of its light waves, a property known as polarization, acts as a historical record of its encounters. If this photon passed through a region of space dominated by powerful magnetic fields, those fields can leave a distinct twist or alignment on its wave pattern. By analyzing this polarization, we can detect the invisible magnetic architecture of the cosmos, tracing forces that shape galaxies but cannot be seen directly. Perhaps the most profound information is written in the photon's path. When its trajectory is gently curved by the gravity of a massive galaxy cluster, an effect we call gravitational lensing, that curved path is not a flaw in the data. It is the data. The specific way the light is bent allows scientists to map the total mass of the lensing object, revealing the otherwise invisible halo of dark matter that surrounds all galaxies. This single photon, in concert with countless others, helps us chart the distribution of the universe's dominant yet mysterious component. It is one voice in a cosmic chorus. No single photon tells the whole story. Astronomers must collect billions of them, patiently assembling their individual data points like pixels in a vast image. Each one is a unique witness, its properties frozen in time since its departure, and together they build a coherent picture of cosmic evolution. The photon we followed is just one such messenger, but its successful delivery of this ancient information transforms a point of light in the sky into a detailed chapter in the grand story of everything. The entire history of complex life on our planet unfolded during this single photon's flight. When this particle of light first leapt into the void, Earth was a turbulent world, its atmosphere thick with volcanic gases and its oceans stewing with the very first simple single-celled organisms. For billions of years, as the photon sailed through the interstellar blackness, our world was busy writing its own epic. Continents slowly collided and tore apart, building mountains and carving seas. Life gradually grew more complex, first clustering into soft-bodied forms in the oceans, then venturing onto land. The great age of dinosaurs came and went, a reign of giants lasting over 150 million years that is itself just a fraction of the photon's journey. The first mammals emerged from the shadows, diversified, and eventually gave rise to our own lineage. The entire tapestry of human history, from the first stone tools to the building of cities, from the rise and fall of empires to the birth of modern science, all of it happened in the last sliver of this photon's travel time. Your own life, and every human life that has ever been lived, fits into a span so brief it is statistically zero against the cosmic calendar of this light. This immense perspective transforms the act of stargazing into something far more profound. When you look at a distant star, you are not just seeing a pinprick of light in the present. You are intercepting a message that has been traveling for so long that its sender may have already flared out and died. You are witnessing a piece of the universe's deep past, a living fossil of an era long gone. That faint gleam in the darkness is a direct, tangible thread connecting your consciousness to events that predate the very ground you stand on. It is a reminder that the cosmos is not just a place out there, but a story in which we are a very recent, yet deeply connected sentence. This fragile thread of light connecting you to the cosmos is spun from pure chance. Every single photon that successfully lands in a telescope or your eye is a cosmic jackpot winner, a statistical miracle that has defied near impossible odds. Its journey was not a guided tour, but a perilous obstacle course where a single misstep meant permanent erasure. First, it had to be born in a star pointed precisely toward our tiny corner of the galaxy. It then had to navigate the galactic maze, slipping through dust clouds that act like cosmic sponges, absorbing the light of its countless siblings. It had to fly past massive stars and black holes without having its path gravitationally slung into a useless orbit from which it could never escape. And finally, in the last millisecond of its billion-year voyage, it had to be the exact right color to slip through our atmosphere's final, filtering gauntlet. For this single successful photon, consider the uncountable trillions that failed. Imagine the blue photons scattered into the daytime sky, the infrared ones absorbed by atmospheric gases, and the untold numbers that were simply swallowed by a random dust cloud in the depths of interstellar space long before our sun even ignited. The starlight we see is not a steady stream but a sparse, filtered drizzle of the most fortunate survivors. This profound element of chance forces a humbling perspective. Our ability to see the stars is not a given. It is a fragile, contingent connection, dependent on a perfect alignment of cosmic circumstances and physical laws. We exist in a rare place and time where the universe has become transparent enough and our world clear enough to allow these ancient messages to get through. The simple act of looking up at a dark sky and seeing a faint, glimmering point is to witness a victory against astronomical odds, a testament to the persistent, against all odds, delivery of stories across the deepest voids. The age of a photon is its most profound secret. While the one we followed is ancient, others are mere infants in cosmic terms. The light from our own sun is only 8 minutes old when it touches your skin, a fresh bulletin from our local star. Yet the faint gleam of the Andromeda galaxy left its source 2.5 million years ago, when humanity's earliest ancestors were just beginning to walk upright. And then there are the most venerable messengers of all, photons that have been traveling for over 13 billion years, arriving from quasars and infant galaxies that existed when the universe was in its raw, formative youth. This incredible spread of arrival times is not a chaotic jumble. It is a perfectly ordered timeline of cosmic history, laid out across the night sky for us to read. By collecting photons of different ages, astronomers do not merely see different objects, they see different eras. They can directly observe how spiral galaxies over billions of years slowly settle into their majestic shapes. They can track the rate at which generations of stars have lived and died, seeding the cosmos with the heavy elements necessary for planets and life. They can witness the universe's accelerating expansion, encoded in the systematic redshifting of the oldest light. Our specific photon, with its particular age and redshift, is a single, precisely dated fossil. Its properties, when compared to both younger and older photons, become a crucial data point. Is its home galaxy more chaotic and blue with star formation than a modern galaxy, or is it already old and red? Does its chemical composition show a lack of certain heavy elements, hinting at a time before many stars had exploded to create them? Each photon is a time capsule, and by lining them up in chronological order, we can watch the universe itself grow up. This is the ultimate goal of cosmic archaeology, using light not as simple illumination, but as the primary tool to excavate the deep past, building the story of everything from the fragmented messages of countless tiny travelers. This finite speed of light is the universe's ultimate governor on information. It dictates that we are forever looking backward in time, seeing the cosmos not as it is, but as it was. That brilliant star you see tonight might have actually died in a cataclysm 1,000 years ago, yet its light, traveling at that fixed, finite speed, continues to arrive, painting a picture of a past that no longer exists. This creates a fundamental limit to our cosmic perception, a horizon in both space and time. We can only observe the parts of the universe whose light has had sufficient time to reach us since the beginning of everything. Beyond that cosmic horizon lies a universe we cannot yet see, not because it is not there, but because its messengers are still en route, their news too young to have reached our shores. This reality transforms our telescopes into literal time machines. We are not just collecting light, we are gathering ancient news. When astronomers point their instruments at a galaxy 100 million light-years away, they are receiving a dispatch from a world that existed 100 million years in the past. The photon's travel time is the very thing that grants us this profound archaeological power, but it is also the wall that prevents us from ever knowing the present state of distant objects. Our entire understanding of cosmic history, from the first galaxies to the expansion of space itself, is built upon this simple, unchangeable fact: light takes time to get here. The photon is the ultimate courier, but it is a courier that is always delivering yesterday's mail, its message eternally stamped with the date of its departure. But this entire epic journey, with its gravitational arcs and dusty labyrinths, is the story we see after the fact. It is the classical tale, the history written down once the final measurement is made. According to the strange rules of quantum mechanics, the photon's reality for those billions of years of travel was profoundly different from the single, clean narrative we have followed. Until the very instant it was captured by your eye or a telescope, this photon did not possess a single, defined path through the cosmos. It was not a tiny bullet traveling a specific route. Instead, its existence was described by a probability wave, a fuzzy cloud of potential spread out across every single possible trajectory between its star and your retina. It simultaneously took the path that curved around a distant galaxy and the path that went straight through it. It traveled the route that skimmed a dust cloud and the one that missed it by 1,000,000 light-years. All of these possibilities were equally real, superimposed atop one another in a state of quantum ambiguity. The photon was, in a very real sense, everywhere at once along all possible routes, its journey an unfurling tapestry of potential. It is only at the final, decisive moment of interaction, the moment of measurement, that this sprawling cloud of possibilities abruptly collapses. In that instant, the universe makes a choice. One specific history is selected from the infinite menu of options, and that becomes the classical, observed path, the story we can then tell about gravitational lensing and atmospheric transmission. The journey we have so carefully traced is the one that was crystallized into reality upon arrival. This quantum weirdness is not a minor detail, it is the fundamental bedrock of light's behavior. It means that the universe at its most basic level does not operate on certainty, but on a tapestry of probabilities. The photon's entire multi-billion-year existence was spent in this state of pure potential, a ghostly presence spanning the void, waiting for a single, conscious observation to pin it down to one specific, tangible history. That furious gamma ray born in the stellar core was a powerhouse of pure energy, but the photon that finally reaches you is a far gentler traveler. This dramatic energy loss is not a flaw in its journey, it is the story of its journey, a permanent record of every major interaction written into its very being. The first and most significant transformation happened during its long imprisonment inside the star. Each time it was absorbed and re-emitted in that frantic core dance, a tiny amount of its ferocious energy was transferred to the surrounding plasma, gradually cooling it from the inside out. This process of countless tiny losses systematically downgraded the photon, transforming that initial gamma ray into a less energetic X-ray, and then further still. By the time it reached the star's relatively cooler surface, it had been forged into a photon of visible light, its specific color a direct product of the star's surface temperature. Its energy was now perfectly tuned for travel, but the universe had one more subtle way to drain it. During its epic voyage across expanding space, cosmological redshift took over. The relentless stretching of the cosmos did not slow the photon down, but it did stretch its wavelength, systematically siphoning away its energy over billions of years. A brilliant blue photon could be stretched to a deep red, and if its journey was long enough, even into the invisible infrared. The vibrant message it carried is still there, but it arrives in a faded, lower energy state. This energy loss is therefore a double ledger. It records the internal physics of its parent star and the external history of cosmic expansion. The photon you see twinkling in the night is a faded relic, its diminished energy a direct measure of both the distance it has traveled and the dynamic, stretching universe it had to traverse. It is a tiny, enduring testament to the forces that have shaped it across the eons. Our single traveler was never truly alone. It was one soldier in an immense, silent army, a ceaseless river of light flowing from its stellar source. Each photon in that river shares the same cosmic birthplace, yet each one lives a unique life. Some were forged deeper within the star's heart, enduring a longer, more chaotic prison break before reaching the surface. Others were emitted from the star's turbulent edges, leaping into the void with less resistance. As this river flows across the light years, its individual members face countless personal fates. One photon might be gravitationally lensed around a massive galaxy, adding a subtle detour to its journey. Its neighbor, traveling just beside it, might be absorbed by a lone, floating atom in the interstellar void, its story ending in silent anonymity. Another might be scattered by a cosmic dust grain, sent spinning off into the darkness on a new, pointless trajectory. For every photon that successfully completes the journey to your eye, billions of its siblings are lost along the way. The steady, unwavering point of light you see in the night sky is not the story of one perfect journey. It is a statistical miracle. It is the average, the collective signal that survives the cosmic gauntlet. The faint twinkle of a distant star is the integrated sum of all these countless, individual sagas of perseverance and loss. When you look at a star, you are not seeing a single narrative. You are witnessing the final, filtered echo of an entire population of light particles, a chorus where only the fortunate few ever reach the stage. This collective nature of light transforms our understanding of every astronomical image. The beautiful, sharp picture of a galaxy from a space telescope is not an instantaneous snapshot. It is a patient accumulation. It is built from the painstaking collection of millions of individual photons, each one a pixel of information carrying a slightly different story from a slightly different time. The telescope must gather enough of these survivors to overcome the random noise of the universe, to weave their individual data points into a coherent portrait. Our own vision works on the same principle. The sensation of seeing a very faint star is not triggered by a single, constant stream of light. It relies on the sporadic, random arrival of just a handful of photons over a few seconds. Your brain patiently waits and assembles these scattered signals into the perception of a steady, gentle glow. That perception is a testament to persistence, a collaboration between the universe's faint output and your mind's powerful pattern recognition. So while the journey of a single photon is a profound epic of physics and chance, its true meaning is only realized in community. It is one voice in a cosmic democracy, one vote in the collective decision that forms our image of the heavens. The story of light is never about one traveler, but about the endless, flowing river of information it represents, a river that connects our present moment to the deep, dynamic past of everything we see. This light is more than a messenger, it is a relative. Every atom of oxygen you breathe, every particle of iron in your blood, was forged in the heart of a long-dead star, a star that shone much like the one that created our photon. The violent death of that star in a supernova explosion scattered these newly forged elements across the galaxy, where they eventually coalesced into new solar systems, new planets, and ultimately into you. When you look up at the night sky and see that ancient starlight, you are not an outsider looking in. You are the universe in a very literal sense, looking back at itself. The light entering your eye is a physical thread stitching you back to your own cosmic ancestry, a direct link to the very furnaces that built the ingredients of life. This connection transforms our understanding of home. We are not merely living on a planet, we are living inside a continuing cosmic process. The photons that have traveled for eons to reach you are completing a cycle that began with the creation of the elements that compose your body. Their journey is the final step in a delivery that started billions of years ago. This realization brings a deep and humbling perspective. Our daily concerns, our personal histories, all unfold against a backdrop of almost unimaginable scale and antiquity. We are transient, yes, but we are also fundamentally woven into the fabric of something eternal. The human drive to understand the cosmos, to build telescopes and unravel the mysteries of light, is not a detached intellectual exercise. It is the universe developing a means to comprehend its own story. We are the mechanism by which the cosmos becomes self-aware. The photon's epic journey from a stellar core does not end in your eye. It continues as an electrical signal in your brain, sparking the thought, the wonder, the profound sense of awe that you feel right now. In that moment of perception, the cosmos finds its voice, and the story of light becomes the story of us. This journey of a photon is one of the universe's grandest narratives, a testament to endurance written across the vastness of space and time. It connects the ferocious heart of a star to the quiet spark of awareness in a living being, bridging the immeasurable gap between the cosmic and the personal. This single particle of light carries within it the story of physics itself, from the nuclear forces that birthed it to the gravitational fields that guided its path and the expanding space that stretched its very essence. It reveals a cosmos that is not a static backdrop, but a dynamic, evolving stage where light acts as both messenger and historian. You are an integral part of this story. The atoms that construct your body were forged in stellar furnaces like the one that created our photon, and your ability to perceive its light is the universe becoming conscious of itself. The next time you find yourself beneath a dark sky, look at any star, no matter how faint. Remember that you are not just looking at a distant point. You are witnessing the triumphant conclusion of an epic voyage that defied near impossible odds for billions of years. That gentle gleam is a survivor, a final whisper from a past so deep it predates our world. Let this perspective fill you with a sense of profound connection and wonder. I would love to hear what part of this incredible voyage resonated most with you. Share your reflections in the comments, and let's continue this conversation about our place in the cosmos.